What if the warm morning light on your face is actually the remnant of a violent cosmic storm? Step just outside our protective atmosphere, and that gentle peace vanishes in an instant. There stands a monstrous engine of pure violence, consuming millions of tons of matter every second. The star we take for granted is actually the most volatile furnace in our solar system. Yet this massive ball of exploding gas somehow holds itself together without tearing apart. To understand this cosmic balance, we must first look at the sheer scale of the monster. Floating 150 million kilometers away, this single object dominates our entire celestial neighborhood. It holds 99.8% of all the mass in the solar system, dwarfing every planet combined. You could pack more than 1.3 million Earths inside its volume and still have room to spare. This colossal mass exerts a crushing gravitational pull that should collapse the star inward. Why doesn't this immense gravity crush the sun into a black hole or a tiny point? Every single atom of gas is constantly being pulled toward the absolute center of the star. Without an opposing force, this massive sphere would implode under its own weight in minutes. Because of this inward pull, a hidden counterpressure must push outward with equal strength. This struggle between two invisible giants creates the stable star we see today. This perfect standoff is a state physicists call hydrostatic equilibrium. Gravity pulls inward, while the intense heat from the core pushes outward with equal force. For 4.6 billion years, this silent tug-of-war has remained perfectly balanced. If the core cools even slightly, gravity wins and compresses the star, heating it back up. To find what fuels this outward pressure, we must dive into the deepest part of the engine. At the absolute center of the sun, we enter a realm of unimaginable extremes. Here, the temperature reaches a staggering 15 million degrees Celsius. The pressure is 300 billion times greater than the atmospheric pressure we feel on Earth. Under these conditions, hydrogen atoms are packed tighter than solid lead. Yet, even at this extreme density, the atoms resist fusing because of a fundamental law of physics. This resistance comes from the fact that hydrogen nuclei carry a positive electric charge. Like matching poles of two strong magnets, they repel each other with incredible force. This electrostatic barrier is known to science as the Coulomb barrier. Even at 15 million degrees, most particles lack the speed to overcome this repulsion. If classical physics were the only rule, the sun would remain completely dark. To bypass this barrier, nature relies on the strange rules of the subatomic world. At this scale, particles behave like waves, their exact positions slightly blurred. This wave-like nature allows them to occasionally slip right through the electrostatic wall. This ghostly phenomenon is called quantum tunneling, and it makes fusion possible. Once they tunnel through, the strong nuclear force takes over, releasing a burst of energy. When 4 hydrogen nuclei fuse into one helium atom, something strange happens to their mass. The resulting helium nucleus actually weighs 0.7% less than the original ingredients. This tiny missing mass is converted directly into energy, following Einstein's famous equation. Every single second, the sun converts 4 million tons of matter into pure radiation. But this newly born energy faces an incredibly long journey before it can escape into space. A particle of light created in the core cannot simply fly straight out. It immediately collides with densely packed ions, bouncing around in a random path. This chaotic, pinball-like journey to the surface takes over 100,000 years to complete. The sunlight warming your skin today actually began its journey during the last ice age. When that light finally reaches the surface, it encounters a highly volatile state of matter. At the solar surface, the extreme heat prevents atoms from remaining intact. Electrons are ripped away from their nuclei, creating a churning soup of charged particles. This superheated, electrically conductive gas is plasma, the fourth state of matter. Because it is highly charged, this plasma responds instantly to magnetic forces. This constant motion of charged fluid generates the most powerful magnetic fields in our system. How does a giant ball of gas generate a magnetic field stronger than a solid magnet? The answer lies in the convective zone, where hot plasma rises and cooler plasma sinks. Because the sun rotates faster at its equator than its poles, these currents twist. This twisting motion of charged particles acts as a self-sustaining magnetic dynamo. When these tangled magnetic fields break through the surface, they leave visible scars. These scars appear to us as dark, quiet patches known as sunspots. They look black only because they are cooler than the surrounding solar surface. While the surface sits at 6,000 degrees, sunspots drop to about 4,000 degrees. Intense magnetic loops choke off the upward flow of heat, creating these cooler zones. But beneath this quiet, dark surface, magnetic tension is building to a breaking point. As the plasma continues to churn, the magnetic loops twist tighter and tighter. They stretch like rubber bands, storing vast amounts of kinetic energy. Eventually, the tension becomes too great, and the magnetic lines snap. This sudden snapping and realigning of magnetic fields is called reconnection. When they snap, they release a torrent of energy that shakes the entire solar system. This reconnection triggers a solar flare, equivalent to millions of hydrogen bombs. Along with the flash of light, the sun launches a coronal mass ejection. This is a colossal bubble of billions of tons of plasma, hurled into deep space. Traveling at millions of kilometers per hour, this plasma cloud heads straight for us. If this radioactive storm hit Earth directly, it would destroy our modern power grids. Yet, our planet survives these violent cosmic assaults thanks to an invisible shield. Deep inside Earth, a spinning iron core generates a massive magnetic field. This magnetosphere deflects the incoming solar wind, channeling it safely away. The only visible sign of this battle is the glowing aurora near the polar regions. But what if we could capture this solar power and build our own star on Earth? For decades, scientists have pursued the ultimate dream of clean, limitless energy. By replicating nuclear fusion, we could power entire cities with zero carbon emissions. Unlike current nuclear plants, a fusion reactor produces no long-lived radioactive waste. But recreating the heart of a star on Earth presents a monumental physics challenge. Without the sun's massive gravity, we have to make our reactors far hotter. Why does an artificial sun need to be 7 times hotter than the real one? The sun uses its immense gravitational pressure to force hydrogen atoms together. Because we cannot replicate that gravity, we must rely entirely on extreme temperature. We must heat the plasma to 100 million degrees so the particles collide fast enough. But no physical material on Earth can hold a 100 million degree fire without melting. To solve this, scientists designed a magnetic cage shaped like a giant donut. This magnetic confinement device is known as a tokamak. Powerful magnetic coils force the charged plasma to spin in midair, away from the walls. By keeping the plasma suspended, we prevent it from instantly cooling down and destroying the reactor. This setup requires the coexistence of the most extreme temperatures in the universe. Inside the tokamak, the hottest and coldest places in the cosmos sit side by side. To generate the massive magnetic fields, the superconducting magnets must be kept cold. Liquid helium cools these giant magnets down to -269 degrees Celsius. Just a few meters away, the plasma burns at 100 million degrees. Maintaining this extreme thermal gradient requires constant, real-time adjustments. Superheated plasma behaves like a living, highly unpredictable beast. It twists, ripples, and tries to break free from its magnetic cage every millisecond. A tiny pocket of turbulence can cause the entire plasma stream to collapse instantly. Supercomputers must calculate and adjust the magnetic fields thousands of times per second. In this high-stakes race, one research facility has pushed the boundaries further than ever. Korea's Advanced Fusion Reactor, KSTAR, recently shocked the scientific community. They successfully sustained 100 million degree plasma for a record-breaking 48 seconds. While 48 seconds sounds short, controlling this extreme state of matter is a massive leap. This achievement proves that long-term plasma control is no longer just a theoretical dream. It also highlights how fusion offers a fundamentally safer alternative to current nuclear power. Traditional nuclear plants rely on fission, splitting heavy uranium atoms apart. This process carries the risk of runaway chain reactions and leaves toxic waste behind. Fusion, on the other hand, is self-limiting and cannot cause a meltdown. If any system fails, the plasma simply cools down and the reaction stops instantly. Even better, the fuel required for this clean energy is virtually infinite. The primary fuel for nuclear fusion is deuterium, an isotope of hydrogen. We can easily extract this resource from ordinary ocean water. Just 1 liter of water contains enough deuterium to match the energy of 300 liters of gasoline. A single bathtub of water could power an average household for an entire lifetime. To scale this technology up, nations are pooling their resources for a massive project. In southern France, 35 nations are building the largest tokamak in human history. This megaproject, known as ITER, aims to prove commercial fusion is viable. It is one of the most complex engineering collaborations ever attempted by humanity. By sharing costs and expertise, these countries hope to unlock the ultimate energy source. But first, engineers must solve the problem of materials that can survive the reactor. The inner walls of a fusion reactor face a constant bombardment of high-energy neutrons. These subatomic particles slowly degrade and weaken even the strongest metals. Scientists are developing advanced tungsten alloys that can withstand this intense radiation. Solving this materials crisis is the final major hurdle before commercial deployment. Once solved, we will enter an era completely free from energy scarcity. Imagine a world where clean energy is so abundant that its cost drops to near zero. Desalination plants could turn deserts green, and carbon capture could run continuously. Geopolitics would no longer revolve around securing oil reserves or gas pipelines. That's why the minutes from that room have never been fully released. This shift will mark the transition from harvesting nature to replicating it. We are currently living through the final chapters of the fossil fuel era. The wind and solar grids of today are stepping stones to a much larger destination. By building artificial stars, we take control of our own ecological destiny. The technology is moving from experimental physics labs to actual utility grids. This leaves us with one final, profound question about our place in the cosmos. Humanity began by shivering around campfires, looking up at a distant, violent sun. Now, we stand on the verge of containing that very same stellar fire in our own hands. It is a journey that took us from quantum mechanics to global engineering coalitions. If we succeed, we will no longer just live under the light of a star. Will the same approach still hold up for the next 10 years?